Hello, today we have a collaboration. This problem was sent to me by Cessna. It's a Russian math YouTuber. So we have a complex analysis problem from Harvard qualifying exam. On his channel you can find what he solved from me. So we have this integral which can be solved using contour integration, and you can see right away that when we pick the contour, it's likely going to be the complex circle. So z of t is equal to e to the power of it. And when we draw the complex plane, 0 to pi is going to be a semicircle. And it's easy to continue to be a full circle. And then we will likely apply residue theorem. Because when we replace cosine of data here, it's going to be something like z plus 1 over z, and then outside of the brackets we need to multiply it by 1/2. So I'm assuming we're going to get some polynomial in the denominator, and then we can apply the residue theorem to evaluate this integral. But first, again, we need to extend the contour, and to do that we're going to apply the fact that cosine theta is symmetrical vertically. So what we're going to do is we're going to take 1/2 of the integral from negative pi to pi of d theta a minus b cosine theta. And now, since I don't want to deal with a bunch of minuses, I'm gonna shift the bounds. We're gonna have 1 over 2 times the integral from 0 to 2 pi d theta a plus b cosine theta. So we get ourselves a nice integral, and what I'm going to do next is I'm going to turn it into a contour one, and for that I need to find the original f of z. So f of z times z prime. Now if you recall, z is equal to e to the power of it, so z prime is going to be just z times I. So I'm going to write f of z times I is equal to 1 over a plus b, and then we have to rewrite the cosine. I'll multiply both the numerator and the denominator by 2 right away. 2a plus b, and here we have z plus 1 over z. Now we can multiply both sides by I to the third power, which is negative I, and we can divide both sides by z. And what we get is f of z is equal to negative 2i over bz squared plus 2az plus b. Now what I'm going to do is I'm going to pull out minus 2i over b. And here we have a pretty simple quadratic left, which is z squared plus 2a over bz plus 1. And now this is f of z specifically, but we deal with 1/2 of the integral, so this all cancels out when we need to just evaluate the contour integral for this over the complex circle and to get rid of the 2 here. So we're just writing it down. It's going to be negative over I over b times the integral over the complex circle of dz over z squared plus 2 times a over b times z plus 1. Alright, and that's our next goal, and when we evaluate this integral we can essentially find the original one. So what I'm gonna do is I'm gonna basically get a new page here, and we're gonna work on solving this integral. So first of all, using the residue theorem, we can do it, but first we need to find the residues, that's for one. For two, we need to find what points lie within the circle. So when factorizing z squared plus 2 over a over b times z plus 1, the thing about it is then it's gonna look in a form where we have z minus a over b plus some root expression over 2 times z minus a over b minus the same root expression over 2. And when we compute the residues for those things, it's actually pretty easy to find using this difference of exactly d. When we paste in a over b plus d over 2 here, we get just d. And when we paste a over b minus d over 2 here, we get minus d. So the residues have been found for different points, which is basically if we have plus d over 2 is going to be negative d, and wait a second, I'll just verify everything. I don't really trust myself here. Okay, when we have plus d over 2 and we plaster it in, then it's going to be just d, and we have minus d over 2 and plaster it, it's going to be negative d. So it corresponds directly. Alright, now let's find what points lie within the circle and what points don't. Well, when we look at a over b plus that root expression, recall how a over b is going to be greater than 1 because they're both positive and a is greater than b. And this root expression is supposed to be a real number, because if we take this part over here, it's going to be 4 times a over b squared minus 4, and a over b squared is going to be greater than 1. So this is going to be greater than 1, and it's not going to be something we care about. Now, if you were to look at this root expression specifically, also, yeah, I forgot to divide by 2 here. But that doesn't change, I think, for now. So now when we subtract it, when we look at this root expression, it's going to be 4 times a over b squared minus 4, and we can bring out the 2. So this simplifies to a simpler root, which is a over b squared minus 1. And when we compare it to this number, and when we bring it out under the root, we get a over b squared, and well, clearly a over b squared is greater than a over b squared minus 1. So this thing is gonna be greater than 0, and what we have to show is that when we subtract the root, it's gonna be less than 1. So let's get started with that. First of all, I'll denote a over b as q. Need to show that q minus root of q squared minus 1 is greater than 1. Now shifting 1 to the left, the root to the right, and then squaring both sides, we get q squared minus 2q plus 1 is not equal, is greater than q squared minus 1. Q squared cancels out. And when we shift to q to the right, we get 2 greater than 2q, which is always true, because the q is going to be greater than 1. So we have proven that this specific point is going to lie within, where we subtract the root. In other words, this z, a over b minus d over 2. And when we plaster it here, a over b minus d over 2 minus a over b minus d over 2 is going to be negative d. So the residue on hand is minus 2 pi I over d. Now recall how d isn't just q squared minus 1, not just a over b squared minus 1. Is we have a 2 here that cancels out here. So what I'm gonna do is I'm gonna get rid of the 2 here, get rid of the d here. It's gonna be a square root of a over b squared minus 1. Alright, and now that we have this on hand, we know that the complex integral, not complex integral, contrary integral over the complex circle z squared plus 2 times a over b times z plus 1 in the denominator is going to be equal to what again? It's going to be equal to pi I over negative pi I over a over b squared and negative minus 1. And now what we have to do is we have to multiply it by negative I b, negative I over b, and that's going to be, when we multiply i's, the negative cancels out, and then we have another negative. We get a negative pi over a squared minus b squared. We're almost there. I made a mistake somewhere. I have acquired a sign that I shouldn't have acquired. Alright, I noticed why. The issue was the fact that, well, in the quadratic formula we could take minus the second coefficient, and then in the factorization process it should become plus again. And now what I have to do is I have to do a bunch of comparisons with minus a over b plus that one roots, that one plus minus that one despicable roots, and I'm gonna bother writing, and we have to show that it's less or greater than something. And the thing is, when we work with the stuff of this form, I can just multiply it by negative 1 and get basically the same thing, but a bunch of signs reversed. So if a over b minus the root was greater than some c, then a negative a over b plus this root is going to be less than c. And essentially what it does is it swaps the rooting. So now I should get the part with another root sign when working with this, and this would lead to the residue being instead of negative pi I over root of a over b squared minus 1, it's going to be without the negative, so plus, and here is also going to be plus. So this is going to be the answer. That's it for today. Sorry for the mistake here. Bye.